I hate entropy too, but we're going to talk about rates of chemical reactions. So looking at the concept of equilibrium, chemical equilibrium involves two ideas, sameness and constancy. So if a chemical system is in equilibrium, then the rate of the forward reaction has to equal the rate of the reverse reaction. And so what do we mean by rate? Well, it's a lot like a rate of speed. It's a measure of how fast the reaction proceeds. Another way to say it is it's the amount of reactant that changes to product in a given period of time. So it could, you could measure that in different ways. You could measure the mass of product per minute that is converted to product, or the moles, or various things like that. We can control rates of reaction if we understand what factors affect them. And there are several factors. Collision theory helps us to understand these factors that affect rates of reaction. So collision theory states that chemical reactions occur through collisions between molecules or atoms. So this makes a lot of sense. In order for two molecules to react, they have to be next to each other. They can't react if they're across the room from each other. And in order for them to react, they have to run into each other with enough energy for the reaction to proceed. Collision energy is related to particle velocity. So you've got, imagine the gases that we had been talking about, because reactions occur in the gas phase as well. So you've got two gas molecules, and when they run into each other, if they're moving very slowly, they collide with little energy. If they're moving fast, they collide with a great deal of energy. Because kinetic energy is 1/2 the mass times the velocity squared. And so the kinetic energy depends a lot on the velocity. Gas phase molecules have a wide distribution of velocities. Some of them are moving slow and some of them are moving fast. The temperature is a measure of the average kinetic energy, or the average velocity of the particles. So you can have high ones and low ones. The high energy collisions will result in reaction. The low energy collisions will not. So you can have two molecules run into each other, but they run into each other slowly enough that they don't react. They just kind of bump off from each other and they go off in their own directions. A higher energy one, they'll collide and they'll actually react. Any questions about those concepts, those ideas? Most chemical reactions have an activation energy, and we'll talk about this in a later chapter. But basically this is a barrier that has to be overcome in order for a reaction to proceed. And so if you think of, let's make up an example. If we use the example of hydrogen reacting with oxygen to form water. Well, hydrogen is a diatomic molecule, oxygen is a diatomic molecule. In order for them to react, a bond has to be broken. So if you've got hydrogen and oxygen and they're running into each other slowly, there's not enough energy in that collision to break the existing bonds. So there has to be enough energy to break the bonds that are already there so that new bonds can form. And there's many different types of, or reasons for activation energy. Another way I sometimes think about this is miniature golf. So here's the miniature golf, and here's the hole. You're trying to get your ball. A lot of times there's this hump, right? They put these little mounds in the miniature golf course. And you have to hit the ball hard enough to get over the hump to have any hope of getting your ball to go into the hole. So if you hit it if you're real wimpy and you just give it a little tap, it'll come part way up the hill and then it rolls back down, right? So that's like the activation energy. You have to have enough energy to get over the hump. So we need enough energy in this collision for a reaction to occur. So then the factors that influence how much energy the particles have are also going to influence the rate of reaction. Because if you have more high energy particles, you'll get more high energy collisions. And then you'll get more reaction, which would mean a faster rate of reaction. So what influences these things? Well, one of the things is concentration. Concentration influences the rate of reaction. In general, the rate of reaction will be higher when you have higher concentration. So here's the example is hydrogen gas and iodine gas reacting to form hydrogen iodide. And so we have little hydrogens and larger iodines, and they have to run into each other. And if there's only a few molecules, if there's a low concentration, there aren't going to be as many collisions. If we have a high concentration, we've got a lot of them in a small area, there are going to be more collisions. And so the rate of reaction is going to be faster. Does that make sense? You can think of the gas particles as people in a room. Let's say we got all the desks out of here, and we had people walking around. Well, the more people we have in here, the more times you're going to bump into other people. If we've only got 3 people in here, you could walk around and not bump into people very much. But the more people you have in the room, the more likely you are to bump into other people. So higher concentration, more particles in that same area or volume, and so you have more collisions. More collisions means a faster rate. Temperature also affects the rate of reaction. Temperature increases the velocity of the particles. They have the same mass. Kinetic energy is 1/2 the mass times the velocity squared, but it increases the speed. So they're moving faster. If we had people running around the room versus walking, there would be more collisions. That's what happens when you get a group of small children together. They run into each other because they're running around the room. They're not walking. And then if you add in having more people and running, there's going to be lots of collisions. And somebody might need to go to the emergency room. You just never know, or at least need an ice pack or something. So when you've got higher temperature, you have more collisions. Not only that, you have more high energy collisions. Because some of the collisions aren't going to do anything. They're too low energy, won't get through that barrier, that energy barrier. When you have a higher temperature, there's more collisions and more of them are high energy and actually do something. And so we see that here we're comparing, we've got the same number of molecules in each of these, but as the molecules are moving faster, we get more reaction at a faster rate. So reaction rates increase with increasing reactant concentration. They increase with increasing temperature. Now, what happens as the reaction goes along? I'm going to go back here. So let's look at this bottom panel. So we've got the iodine and the hydrogen combining. When a reaction occurs, then the hydrogen and iodine are done. Those 2 molecules are done because they've made hydrogen iodide. And those guys are doing their own thing. So as the reaction goes on, what happens to the concentration of the reactants? It goes down. When the concentration goes down, the rate goes down. Okay? So reaction rate will generally decrease as the reaction proceeds because there's less reactant to react.